Hello everyone, and welcome to this video on section 2.4 called Arc Length of a Curve and Surface Area. So in this video, I'll be taking you through a sample version of a Newton-Alta assignment for section 2.4, on this arc length of a curve, and also the surface area of a surface of revolution. And I'll explain later in the video what that is. So here's what your Newton-Alta assignments look like, right? You got the title of the assignment up top. You won't see the word preview. You have your mastery bar in the upper right corner telling you how far along you've gotten. Your activity log, which shows you how far you've gotten in each objective. So it looks like there are 4 objectives broken up into 2 parts. So we'll be seeing all the arc length questions first, and then after that, the area of a surface of revolution questions. And then every question is related to a certain objective, right? You have a current objective, a question to go along with it. And then at the bottom of every question, you should have a feedback button. If you notice a typographical error or something wrong with the question you're dealing with, you can send feedback directly to Newton, and hopefully they can fix things. You will not see this instructor cheat button. This will not be there, okay? But you should then see a more instruction button. Click on that if you're having trouble with a particular objective, and you'll be taken to a page with some videos to watch or reading to do, one or the other or both. And then you'll be given questions, related to that objective, where while you're working on the question, you can still go back and refer to the instruction, and perhaps that will help you get through the assignment. And as always, the questions I see here in this video may not be the exact same questions you see when you work on the assignment yourself, but I'm hoping they're similar enough for watching me do them here. They'll help you out a bit, when you work on the assignment on your own. Alrighty. So this first objective, determine the length of a curve given as a function of y, where x is a function of y between 2 points. So they're telling us to let g of y, or x, equal 2y squared. We're going to calculate the arc length, right, the length of the curve over the interval 1 to 5. I'm hoping, is that the interval from 1 to 5 on the x-axis, the y? It does say over the interval. Well, since they're giving me everything in terms of y here, I'm going to say this is on the y-axis. Okay. Now we'll see if we get it wrong later, then it must be on the x-axis. So I'm going to draw a picture of the piece of curve they are talking about here. And then they say, use a calculator to approximate the value of the integral. Round your answer to 4 decimal places, right? So the integral we're going to set up more than likely won't be a very nice one. There are some integrals out there that cannot be expressed in terms of the elementary functions, right? Your polynomials, your rational functions, radicals, exponentials, logarithms, trigonometry, inverse trig, right? Those are the elementary functions that you learned in pre-calculus, right? There are integrals out there that you'll come across that can't be expressed in terms of those elementary functions. So probably going to see one of them here and then have to go to a calculator to round our answer to 4 decimal places. So to some paper. So I will draw this curve they're describing. So here's your xy plane. Right, they gave me this function, g of y was 2y squared. And again, they gave me an interval. Now I'm going to assume, we'll see if we get it wrong later, but I'm going to assume that that interval, because we're given a function in terms of y, that's an interval on the y-axis, right? So I'm going from 1 to 5 here. If I'm wrong, I'll change it to 1 to 5 on the x-axis and then redo it. All right, so when y equals 1, x, this is x over here, g of y. When y is 1, x would have to be 2. Right, so you got 0.21 is on this curve, and when y is 5, right, 5 squared is 25 times 2 is 50. X would be 50. So the 0.55 over here. Now, the only reason I think it's on the y-axis, these values, is because if these were x values, y would be some weird square root numbers. I'm not saying that that's wrong. You can always involve square roots. It's just I feel like it would be, they're not trying to whip you up too much right away. And then x equals 2y squared, right? That's a parabola opening to the right with a vertex at the origin. So this isn't a great drawing. It's not to scale. It's, something curvy. This is not a straight line. Right? This is not a straight line. But there's our curve. Right? Okay. Here's how we're approximating arc length, right? The length of a curve, they're calling the arc length. And arc length will be represented by the letter S in this particular text. I know other texts probably use other letters, maybe like little L for length. But I've seen in most texts, and this one especially, that the Newton Alta assignment refers to, they're using S to represent arc length. So we're looking for the entire length of this piece, right? If I started at this point and walked along the curve to this point, how far did I go? That's what we're asking for. So this whole length here, right, called S. Well, just like with most, you know, things in calculus, when we're trying to find, say, the slope of a tangent line or the area under a curve or the volume of a solid of revolution, right? You took a little piece of the thing you're looking at. All right, so if I were to go to some y value here, between 1 and 5, go over to the point on the curve that corresponds to that y value. All right, that would also correspond to some x value between 2 and 50. Take just a tiny piece of that curve around that point, right? So I'm going to make this a little different color. Now, it should be tinier than this, but basically it's going to be pretty much like imagine this is the tangent here. It's the tangent line. Remember, the tangent line closely approximates the curve at a point, right, if we're really close. And the length of this tangent line, we'll call, you could call it delta S, right? Some little tiny change in the arc length. But because we're going to have that shrink to 0, it's called ds, right? So this is some little ds here, some little piece of the arc, little piece of the curve. So over here, I've got this picture. So here's that little piece of curve. I'm taking this over here. Got a length at ds. Well, I can break this up into its horizontal and vertical components this way. This ds, right, the horizontal component is the change in x, which I'll call dx. And the vertical component of ds, we call dy, right? It's a little tiny change in the y coordinate. And so we're seeing from over here in this picture a little right triangle. And we have ds, right? ds, the length of little ds, that little piece of arc, that little piece of curve, is just, by the Pythagorean theorem, square root of dx squared plus dy squared. right? Just using the Pythagorean theorem on that. And I would take this little piece of, arc here and all the little pieces of arc, right? For every y value from 1 to 5, or for every x value from 2 to 50, right? I'm taking these little pieces of arc and adding them all up to create the entire length of the curve. Right, so arc length, right? The total length of an arc, they'll say it's the integral of all these little ds's. Adding up, remember, integral is summing things, right? It looks like a big elongated S. You're summing up all these little pieces of arc, these little ds's, to get the whole arc itself. And we just said that, ds can be expressed in terms of dx and dy, the horizontal and vertical components, right? We like things horizontal and vertical when we're talking about rectangular coordinates, right? X's and Y's. So I'm going to rewrite ds here as, the square root of dx squared plus, dy squared. And using this, I can write this arc length integral in terms of both dx and dy. So we can do our integral with respect to x or with respect to y. So if I want to do an integral, say with respect to x, now I'm going to do with y here, but I'll show you both. If I want to do it with respect to x, that means I want an integral with a dx, something times dx. Well, can you see from this, right? Again, I'll call arc length s. Right, so we have s equals arc length equals, and we have our integral of the square root of dx squared plus dy squared. Now, in this expression here, if I were to factor out dx squared, you'd have dx squared, the dx squared pulled out. And then if I were to do that, you'd have 1 plus, and then, dy squared over dx squared, which can be expressed this way, dy over dx squared, like that. It's dy squared over dx squared. And then the square root, break up the square root of a product, right? Make it the product of the square roots here. This will be real. The square root of dx squared is, dx. And we'll say it's, it technically should be the absolute value of dx, but we'll have dx be some positive number here. So I'd have finally the integral, and since we're integrating with respect to x, I'm going to go from x equals some value a to x equals some value b, right? And here that's going to be from 2 to 50 if I'm doing with respect to x, of the square root of 1 plus, and then this dy over dx, right? I can call that y prime. Y prime with respect to x squared. And then at the square root of dx squared is just dx. On the outside, I have just times dx. So this is one arc length formula. All right, if I have y equals some function of x, right? If y is some function of x, then I just put the derivative of y here, right? And square it, add 1, take the square root, and then we're integrating over the x values, right, that curve is over. So yeah, this curve is over 2 to 50. So that's with respect to x. Now I could take the same integral, right? Or set it up another way, right? Do it with respect to y. Meaning that y is the independent variable now. So x depends on y. X is a function of y. So maybe I should have put that up here, right? With respect to x means that y is, some function of x, right? And y prime, right? Y prime would be called f prime at x. That into my formula here. So the other way is to, what if I do it with respect to y? Right, so that means y is independent. x would have to be some function of y. Now they're calling it g of y. And you'd see we'd call x prime g prime at y. But yeah, so the arc length, still the same start, right? It's still this integral of the dS's, adding up all these little pieces of s, right? Which is this. So it's the integral of the square root of dx squared plus, and then dy squared. Now, if I want to get this to be an integral to, something times dy, I take this expression of the square root, factor out dy squared. So it's the integral of the square root of dy squared. And if I pull dy squared out, then we'll have, dx over dy, but that would just be x prime, right? Because again, x is in term of y. We're doing the derivative of x with respect to y. So this dx over dy, I'm going to call x prime or g prime of y on the next line. Then plus 1. Oh yeah, sorry, this is squared, right? Because it was dx squared over dy squared. So dx dy squared. And then plus 1, right? The dy squared came out. All that under the square root. And then when I do the square root of a product is the product of the square roots here. We're getting the integral. And, this is going to be over, again, with respect to y, these are values of y here. So from y equals some value c to y equals some value d, which in my picture up here, the y values I'll be integrating over, that this curve is over, is from 1 to 5, right? So I'll have 1 to 5 for the limits. And then times the square root of, here this is x prime squared plus 1 or 1 plus x prime squared. Again, this is x in terms of y, g prime of y, x dx dy, right? And then, the square root of dy squared would just be dy. So you got times, the dy out here. Right, so there's your two arc length formulas. And you can set up both. If you know the x interval that you're over or the y interval that you're over, you can set up either one of these. It depends on what's easy, can you write y as a function of x? Or can you write x as a function of y, for that particular curve? And depending on which one you are more capable of doing, you'll set up the corresponding integral to find the length of the curve, the length of the arc. All right, so keeping these in mind, I'll keep bringing these up as we go through other examples. Let's find the length, or at least set up the integral for the length of this piece of curve here. So we were given x equals 2y squared. Now, since y is if I have x as a function of y is the independent variable, I'm going to find arc length using that one that we're integrating with respect to y. So from y equals, 1 to 5, y equals 1 to 5. Remember, this is the square root of 1 plus, and then x prime squared. And it's all inside the square root, and then times your dy. All right, so what is x prime, right? If x is 2y squared, right, the derivative of x with respect to y would be just 4y. 4y. I'm putting 4y in here. Okay, so this is now the integral from 1 to 5. Again, this is y values, right? Y equals 1 to 5 of the square root. And then inside this square root, 1 plus, and then your x prime we said was 4y. And this is being squared, right? Times the dy on the outside. And simplify this a tad. Okay, this is the integral from 1 to 5, y equals 1 to 5, the square root of 1 plus, and then this is 16y squared. And then the dy on the outside. Okay. So there's the arc length. written as an integral, right? This would give me the length of that curve that I drew from this point to that point. How far did I travel? Now, they told us to, round to 4 decimal places. So I can just enter this now into a calculator. I'm going to go to that Desmos website, desmos.com. You've probably seen it in previous videos of mine. Now, let me tell you this. This integral here, at the moment, right, at this point, we're in sections, chapter 2 of whatever text Newton Alta is using here. At this point, we have not seen a method of integration that would really help us out all that much here. But later on, right, we'll see in the chapter 3 videos I put out, we'll see some techniques of integration that we can use to actually integrate this, find the antiderivative of the square root of 1 plus 16y squared. Yeah, this is actually doable. As I said at the top of the video, though, you may come across integrals in your career that aren't expressible in terms of the elementary functions, right? But this isn't one of them. But that's neither here nor there, right? They only asked us to round this to 4 decimal places, right? So I'm gonna go to that Desmos site, right? Here we go, desmos.com, right? And then off to the side, right? You can just enter an integral, just put int, and some definite integral will come up, going from lower limit 1 to upper limit 5 of, and then for the square root, you can just type sqrt. Square root symbol pops up, and then inside that square root, I had 1 plus 16y squared. So that's all in the square root, and then get out of the square root, move your right arrow a couple times, dy. All right, and then rounding this to 4 decimal places, right, the nearest 10,000th, 48, 202, 2002, 5. Right, the 5th decimal place is 5 or higher, so I bumped the 4th decimal one up 1 unit, or one number. So 2003, right, 48.2003 is what I shall enter. Right, so putting here approximately 48.2003. And like I said, I hope this is an interval on the y-axis. If it's not, we'll have to change it up and then submit. Wonderful. So it was an interval on the y-axis. Okay. So remember what I said earlier. I'm going to do this same one. We'll get the same answer. But I just want to show you that all these arc lengths you can set up with respect to x or with respect to y. So let me show you. The same problem. Okay, same problem. Now I'm going to do with respect to x instead, right? This was with respect to y. You had the dy. Now, when I do it with respect to x, right, remember this piece of curve that I drew is from x equals 2 to x equals 50, right? So when I set up the limits of integration, it's going to be from 2 to 50. So we have s, right, equals, let's separate these. Right, it's going to be the integral from x equals 2 to 50 now of the square root of 1 plus, y prime, right? We're going to try to get y in terms of x, 1 plus y prime squared, and then, times the dx outside here. All right, so we saw earlier x was equal to 2y squared, right? If I solve this for y, you got y squared equals half x, or x over 2. And then y could be either the positive or negative, square root of x over 2, which our curve here has positive y coordinates. So for our curve, it's the positive square root, right? Our curve is this, y equals, I'm going to write this way. This will be 1 over the square root of 2 times x to the half. It's square root of x divided by square root of 2. Square root of x is x to the half, and I'm just going to leave the 1 over square root of 2 as 1 over the square root of 2. In the arc length formula, I need y prime. So what's the derivative of y with respect to x? Y prime, right, would be still this constant, right? 1 over the square root of 2 is a constant. And then I'm using the power rule here. This would be 1 times a half x to the negative half, right? You subtract, multiply by the power, subtract 1 from the power. Okay, so this is 1 over 2 root 2, which is also the square root of 8, yeah, times x to the negative half. And that's going to go into y prime here. Right, so my arc length integral, s, right, arc length s, integral from x equals, we said 2 to 50, 2 to 50 of the square root of 1 plus, and then this y prime, 1 over 2 root 2 times x to the negative half squared, right? It's the y prime squared, and then times, the differential of x outside. And after simplifying this, right, this will be the integral 2 to 50 square root of 1 plus, I said the 1 over 2 root 2, when I square that, that'd be 1/8, and then x to the negative half to the second would be x to the negative first. And then times the dx on the outside. And you can simplify this a tad, right? Make this 1 over 8x. So it'd be 8x plus 1 all over 8x. And yeah. Again, something I feel we could do later with other method. We only know really u substitution at the moment, right? Later in chapter 3 material, we'll see some techniques of integration that may assist us in an integral like this. All right. Yeah, so I'm going to enter this now and show you that, we should get the same thing as before. Should get the same 40, it's just the same curve, right? So we should get the same length. So I have the integral. Now my limits this time, lower limit was x was 2 up to x equals 50. And then the integrand was the square root of 1 plus, and then I'll just go 1 over 8x, right? Because it was 1/8 times x to the negative first. And then get out of there, times dx, and you're seeing, indeed, these are the same number, 38.2003 if I round to 4 decimal places, right? So just for this first one, right, I'm only going to do this really for this first one. Unless later, you can play around with these. Try setting it up with respect to x, and if that looks ugly, if the integral isn't nice, maybe try, setting it up with respect to y instead and see if that's a nicer looking integral. Because I'm sure there will be some problems where we'll be asked for an exact answer, right? So we'll have to figure out what the integral is. For right now, we're just approximating. Wonderful. So again, after every question, right, there's, whether you get it right or wrong, there's an answer explanation. Please read through these, whether you get it right or wrong. If you get it right, just skim through it just to see, if they did anything different, right? If they did some sort of weird method that you might like better. Of course, if you got it wrong, go through it, try to figure out where you went wrong. And hopefully that'll help you for future questions. All right, next. So this one, they're just asking us to set up the integral, and notice there's a dy here, so I must put it in terms of y. Set up an integral that represents the length of the curve given below, so this curve here, over the interval from y equals 3 to y equals 7. right? Do not evaluate the integral, right? They just want us to set it up. All right, so you could draw this curve, right? The thing is, though, you don't really need to draw the thing. I know I drew it for the first question, but you know, we're given this curve here. E of y equals 5y squared plus 3y minus 4. And over the interval, or I'll just say on interval y belongs to, they said from y equals 3 to 7. So I'll draw a very, very rough sketch. All right. I know this is some parabola, right? This is x equals some quadratic. So it's going to be a parabola. And because it's got a positive coefficient, it's going to be a parabola opening to the right. But only part of it, though, from when y equals 3, right? So y-axis, x-axis, from y equals 3 to y equals 7. All right, now when y equals 3, you can pop stuff in here, right? This is 5 times 9, and that's 45, and then plus 9 is 54, minus 4 is 50. All right, so when x equals 50, y equals 3, and when y equals 7, all right, let's see, if I pull a y out of these, do like a little synthetic division, 5 times y plus 3, 35 plus 3 is 38, and then times 7 would be 210 plus 56, 266, minus 4, I think that's 262, all right, or 5 times 49 is 245, plus 21, 266 minus 4, 262, right? So when y is 7, 262, and again, it's just some parabola. It's just it's like my previous picture, right? This is not a straight line, right? This is not a straight line. It's some piece of a parabolic curve. This is a crappy picture, not to scale by any means. And we want this, right? How far is this? What's S? What's the arc length? How far is it from, if I travel from here along the curve to here, how far did I walk? How far did I move? Now, because everything's in terms of y real nicely, they give me x in terms of y up there, I can easily just go, what's x prime in terms of y? That'd be 10y, 10y using the power rule, 5 times 2, y to the first, plus 3. 3y would just be 3, and then minus 4, that would have a derivative of 0. And then our arc length, if I'm doing everything in terms of y, it's going to be the integral from, our y values here over this piece of curve are from y equals 3 to 7. And then square root of 1 plus x prime squared, right? And then times the dy out here, right? And x is a function of y. And I'm putting this in for x prime, this quantity 10y plus 3. This is the integral from y equals 3 to y equals 7 of the square root of 1 plus the quantity 10y plus 3 squared, and then, times the dy on the outside. And this is it. Okay, this is all they want you to do. Write this in. Now, if you were to actually expand that, multiply this expression here out, you'd have 100y squared and plus 60y, right, 30y twice, and then plus 9 plus 1, maybe plus 10. Right, you can write that out as well inside the square root. So I'll do that. That'll be probably faster to type because I don't have to do parentheses and stuff. So back here, right, the lower limit, y equals 3, upper limit, y equals 7. And then in here, right, you got square root, and then inside that square root, I had 100 y squared plus 60y, and then plus 10. Oops, that should be in the square root. That should be in the square root. All this in the square root plus 10. And that should be good. That's all they want. Great. Yeah, read through the answer explanations real quick, and we'll move on. All right, so those last two examples, right, we were given a curve where x was some function of y, right? You had g of y. This is where we're given curves that are, where they're defined as functions of x, right? X is considered the independent variable. So it's the same thing, but just with all x's and dx, and we're setting up the integral. All right, so once again, I'll draw a rough sketch of some piece of this curve, right? We have f of x equals, or y equals, negative 3x squared plus 2x minus 1. This is some parabola opening down on the xy plane, and we're only looking at the piece of it, though, from when x equals 2 to x equals 5. So f of x equals negative 3 squared plus 2x minus 1. And this is the same as y equals. And we're on the interval from x equals 2 to x equals 5. So if you want to plot points, right, x equals 2, this would be negative 12 plus 4, negative 8 minus 1, that's negative 9. So 2, negative 9. And when x equals 5, be negative 75, right? 5 squared is 25. Negative 75 plus 10, negative 65 minus 1, negative 66. Right, negative 65 minus 1. So at 2, you got negative 9 as an output. At 5, negative. You don't have to do this. What I'm doing, remember I said last problem really briefly, you don't have to draw these. Okay, you don't have to draw a curve to know how long it is. And then it's some parabola opening down, right? So this would be some concave down curve. Again, very, very rough. This is not great, but there's our curve, and we're trying to find its length, right? How long is this units? Now everything's with respect to x, right? So my arc length integral is going to be, integral from x equals, right? The interval, all the x values for this piece of the curve here are from 2 to 5. So integral from 2 to 5 of the square root of 1 plus, and then, y was a function of x, so y prime here is squared, and then times, dx on the outside. That's a dx. Sorry, it's tiny. So I just need y prime. Y was this, so y prime, right, dy over dx would be negative 6x plus 2. Okay, and that's going in here. So it's the integral x equals 2 to 5 of the square root of 1 plus, and then our quantity, our y prime, negative 6x plus 2 squared, and then, dx on the outside. And this is fine. You should be able to just enter this. Go ahead and try it, right? As long as what you're entering is equivalent to the correct result, the Alta system should give it to you. But, I like to let's simplify this a little bit here. If I were to square this, right, you'd have positive 36x squared. Then you'd have negative 12x, but twice, so minus 24x. And then plus 4 plus 1, right, you got plus 5. So I'm gonna type that in the square root. And that's all they want, right? The lower limit, x equals 2, upper limit, x equals 5, and the integrand, the square root of 36x squared minus 24x plus, it's outside the square root again, plus 5. All inside the square root. Check it out. And again, answer explanations. All right, moving on. Looks like we're just going to be bouncing back and forth between these, right? So here's another one. Okay. Now you don't need set up an integral this. Notice the function given to me here, again, it's a function of x, so I'm going to do the integration with respect to x again. Right? Everything's in terms of x. Y is equal to 2x minus 4. This is a line. Remember, linear functions are very easy to work with, right? If I have a piece of a line, I should be able to find how long the piece is without setting up an integral. I'll still set up the integral, but show you also, what I would do without setting up the integral. So let's over the interval 3 to 7 here. Let's graph this. So yeah, this will be a straight segment, right? Something straight. So we're given this curve, right? F of x is 2x minus 4, right? That's the same thing as y equals 2x minus 4. Just on the interval, though, from 3 to 7. So here we go. 3 on the x is 7 on the x. Now, when x equals 3, that's 6 minus 4, right? The y value is 2. There's that point on the curve. And when x equals 7, right? 14 minus 4 is 10. 7, 10 would be on the curve. And it's a linear function. So this is a straight line. Right? This is straight. And what's s, right? What's the length of that segment? Well, this is 4 units across, 3 to 7. And go straight up. This is 8 units up. Got a right triangle here. So s is the square root of 8 squared plus 4 squared, right? You don't need an integral for a straight line. Just the distance between these 2 points. And that's the square root of, 64 plus 16, the square root of 80. And that's it. Now, notice in the instructions, right, they said enter an exact answer, right? No calculator work. Now this, of course, could also be, this is the square root of 16 times the square root of 5. So this is 4 times the square root of 5, right, if you simplify the root. Units, right? And these are all units, by the way, right? We're talking length. It's length, so it's not square units, it's not cubic units, right? It's not an area, it's not a volume, it's a length. So just plain old units. All right, so that's without the integral, right? That was very, very, very easy. Now with an integral, right, if you're doing your arc length integral, or the arc length here, it's going to be the integral from, I'm doing this over values of x, right? Everything's in terms of x. X is the independent variable. From x equals 3 to 7, of the square root 1 plus, and then, y is a function of x. Y depends on x, so this will be y prime squared, and then times your dx on the outside. Now, y prime is simply 2, right? Y is 2x minus 4. Y prime in terms of x would just be 2. So we're going to get a constant here, right? This is very simple. So it'll be the integral 3 to 7 of the square root of 1 plus 2 squared, right? Y prime is 2, and then times dx. Now 2 squared is 4, plus 1 is 5, and then the square root of 5 is a constant. The constant multiples I can pull out. That's the square root of 5, times the integral from 3 to 7 of just 1 dx, which would be the square root of 5. 5, square root of 5, sorry, that's a 5. That's a 5. Times, and then the antiderivative of 1 would just be x, right? And then we're going from x equals 3 to 7. So we have the square root of 5 times, and then 7 minus 3, which is 4. And I get exactly the same thing I got earlier, right? With just looking at it as a big right triangle instead of breaking it up into little pieces and integrating. All right, so yeah, straight lines should take less time. So we have 4 times the square root of 5 units long. 4 times square root of 5. Exact answer, right? No rounding, no calculator. Great. So they went through the whole integral. Yeah. All right, next. So this is the other way around. So I'm going to do this integral with respect to y. We're given the curve as a function of y and some interval on the y-axis, right? And again, it's a straight line. This is a linear function, right? Negative 3y minus 4. So it's just the distance between 2 points, straight line distance between 2 points on the xy plane. So I'll show you here. So I'll do it both ways again, right? You got g of y is, negative 3y minus 4. And we're on the interval on the y-axis, from 2 to 7. So if I draw this, right, when y equals 2, right, up to y equals 7, when y is 2, this would be negative 6 minus 4 be x would be negative 10. Let's say that's over here. Actually, no. Let's put negative 10 here. So you have the point negative 10 comma 2 on the curve, and when y is 7, this would be negative 21 minus 4, that's negative 25, right? So let's say there's a point there. And it is a straight line. This is a linear function. And what's s, right? What's this arc length? Well, and I can break this up pretty easily into horizontal and vertical. If it's a straight line, I can just make a big right triangle. Say this distance here is, 15 units. This distance here is 5 units, right, from 2 to 7. And so s is the square root of 15 squared plus 5 squared, which I'm going to do this thing here. Now, 15 is 3 times 5, so that's 3 squared times 5 squared, right, plus 5 squared. And then I can factor the 5 squared out, and the square root of 5 is 5. And then what we'll be left with is, 3 squared plus 1, 9 plus 1, you have the square root of 10 left over. Right? I kind of rushed that, sorry. But there's your exact value for the length of this piece of line, right? 5 times the square root of 10. Or, right, like let's say the arc length is the integral. We're doing y's here, right, from y equals 2 to 7 of the square root of 1 plus, now, if y is the independent variable, right, integrating with respect to y, then x is a function of y. So this will be x prime squared, and then times dy out here. And this was x. X was given as, negative 3y minus 4, right? So x prime is once again just a constant. It would just be negative 3. So I plug in negative 3 here. That'll go from 2 to 7. The square root of 1 plus negative 3 squared. And this is just the square root of 10, right? So this would be the square root of 10 is the integral from 2 to 7 of just 1 dy, right? Pulling the square root of 10 out. And this is just 5, right? This would be y, and then you plug in 7, plug in 2, subtract, right? This is 5 times the square root of 10. Exactly what I got earlier when I looked at it as just some big right triangle. 5 times the square root of 10. Sorry, my 5 looks like an S there, but it's 5 times the square root of 10 units long. Check it out. Wonderful. And again, read through this, and let's continue on. So this next question, same deal. All these are arc lengths for a while. So here we're given another function in terms of y, right? So y is the independent variable again. X equals y to the 4th over 8 minus 2 plus 1 over 4y squared. And we're asked to, calculate the arc length over this interval. And again, it's an interval on the y-axis now, because everything's in terms of y, from 2 to 3. And notice it's enter an exact answer. So the integral we set up should be doable. So I'm not even going to draw this curve anymore. You got from y equals 2 to 3. We're given the curve because I could give you a rough sketch of the curve, but it wouldn't be. I mean, we could look at it. We could look at it in Desmos. So I guess I'll do that. I'll do that at least instead of drawing it by hand every time now. We got y to the fourth divided by 8, which is the same thing as 1/8 times y to the fourth minus 2 plus, and then 1 over 4 y squared. So again, just to make, this is x equals, right? X equals some function of y. And we're on the interval where y is going from, 2 to 3. Now, if I want to rewrite this to make the derivative a little easier, because I'm going to need the derivative, I need x prime in my arc length integral. This is 1/8 y to the fourth minus 2. And then this last term is a quarter for coefficient. And then, 1 over y squared is the same thing as y to the negative second, right? All right, so that'll make the derivative a little easier. And in the derivative, I'm going to need x prime, right? I need dx over dy. Sorry, x prime, not x squared. It's prime. And I'm just going through. It's a nice little, almost a polynomial here, like one power rule throughout. So this would be a half, 4 times an eighth, y to the third, plus nothing, right? Constant -2, and then minus a half, y to the negative third. Okay. So the length of the arc. Well, let's actually look at what this looks like. Just real quick. Again, you don't have to draw the curves, but let's say you have a rough idea as to what it's looking like from a previous problem. So I'll enter the curve we were given, right? It's x equals, y to the fourth over 8 minus 2 plus 1 over 4y squared. So this double sideways parabola looking thing. And I'll just change the window up here so that the y values are from 2 to 3, right? We're only looking at the piece of this curve from y equals 2 to y equals 3. All right, so that's it there. Just this. I'll make it a little bolder. Here we go. Just this piece of curve right here, the top, from the top to the bottom. We're asked how long is this? Okay. So back to the paper. Gonna be the integral, right? From y equals 2 to 3 of the square root of 1 plus, and x is in terms of y, so we got x prime here squared, and then dy on the outside. Found x prime and putting it in here, right? So this is equal to the integral from 2 to 3 square root 1 plus, and then the quantity, right? This x prime I found here is half y cubed minus half y to the negative third. Right, that's being squared. Okay, and then times dy. Multiply this out. If I were to multiply this out, right, I'll do this in a different color. You'd have a quarter y to the sixth. And then when I multiply these, I get minus a quarter y to the 0. So minus a quarter, but I'd have two of those, right? So negative a quarter twice, so minus a half. And then multiply this last term by itself, right? Positive 1/4 y to the negative sixth. All right, this is what I get when I take half y cubed minus half y to the negative third and square it. Now, if I combine, common terms in here, the only constants, 1 minus a half, we're getting the following. So all together, this is going to be 1/4 y to the 6th plus a half, right? 1, and we got this minus half here, plus a half, and then, the rest of it plus a quarter y to the negative 6. Now, hopefully you notice something. I pointed out, of course. All right, when I square this, 1/2 y cubed minus 1/2 y to the negative third, I got this and this with minus a half in the middle. You see this expression on the bottom here is this same expression, but with plus a half in the middle. Right, so this expression finally is just half y cubed, the quantity half y cubed, and then instead of a minus here, plus half y to the negative third squared, right? And check it out. If I were to square this, right, you get a quarter y to the 6th, and then half y cubed times a half y to the negative third would be 1/4. We have two of those, right? So plus a half plus 2/4, that's the middle term. And then a half y to the negative third would be a quarter y to the negative 6 when you square it. And we're taking the square root of this. We're taking the square root of this square. So the squares will go away and I'm left with the following, right? So I'm going to square right the resulting term after that, the resulting expression. So this is the integral from 2 to 3 of, and again, the square root will be gone. It's the square root of this quantity squared. So it's just this quantity here, just 1/2 y cubed plus a half y to the negative third. That's it. Square and the square root undo each other. Now, technically, it should be absolute value, but you saw in my piece of the curve from when y is to, all these values positive. All right, these are all positive, so I don't need absolute value around that. And then times the dy, right? You still have the dy out there. Great. And these are some things I can use a simple power rule for to anti-differentiate. This is a half times, 1/4, 1/4 y to the 4th. So that's an 8th y to the 4th. Right? And here I'd be raising the power, right? Y to the negative 2nd times negative half, so that'd be minus a quarter y to the negative 2. And then we're going from y equals 2 to y equals 3. And this here, this 1/4 y to the negative 2, I'll think about that as 1 over 4y squared. Think about it that way. So we have 1/8 y to the 4th minus, and then 1 over 4y squared. I plug in 3. All right, now when I plug in 3, 3 to the 4th is 81. Let's see that, 81/4 minus, and then 1 over, 3 squared is 9. 1 over 4 times 9, that's, sorry, 81/8. 81/8. And then 1 over 4 times 9, right, that's 1/36. Right, so there's the value at y equals 3 minus, and then the value at y equals 2. Now 2 to the 4th is 16, but 16 divided by 8, is 2. And then 1 over 4 times 2 squared, 2, that's 1/16. Okay, so let's do some simplification here. Now both of these have a quarter in common. And then you'd have 81/2 minus, and then 1/9. And I'll get a common denominator. Multiply by 9 over 9 here, and 2 over 2 here. It's a quarter. 729 minus 2 over 18. So that's 727 over 18. So this is 727 over 40 and 32 over 72 minus 2 would be 32 sixteenths, right? Minus 1/16, and that's just 31 sixteenths, right? So minus 31 sixteenths. And then I have to do the common denominator again, right? That's 72. It's 8 times 9, that's 2 cubed times 3 squared. 16 is 2 to the 4th, right? So to get a common denominator, multiply this by 2 over 2, and this, that'll give me the 2 to the 4th down here. And then this by 9 over 9, right? That'll give me 3 squared down there. Okay, almost done here. And I guess I could have just gone to Desmos if I knew this was going to be rational. But I'm already almost there, right? Might as well keep going. So yeah, so 2 times this would be 1454 minus, and then 279 all over, and then 9 times 16, or, you know, that's 90 and 54, 144. Okay. And then finally, let's subtract these. So this is like subtracting 300 and then adding 21. So that'd be 1154 plus 21, 1175 in the numerator, divided by 144 in the denominator. And this has no factor of 2, and it's not a multiple of 3 as well. All right, so this is it. Units, right? This is plain old units. That's the length. Okay, and then I really want to double check myself there. When there's a lot of arithmetic like that, I just want to make absolutely certain. So let's put in the integral that I had back in Desmos. We had the integral from 2 to 3 of, and then I had y cubed over 2, right? Half y cubed plus, and then half y to the negative third. So y to the negative 3 over 2. Close parentheses on that. Be y. And see, it says I can. You can't see it. It's on the left side here, but there, right where my cursor's flashing, right, going back and forth. Hopefully, you can see that by the upper limit of the integral. There's a change to fraction button, and yes, you see it's 1175 over 144. Yeah. So in the future problems in this video, if I notice that something's going to be rational, it can be expressed as a fraction. I'm just going to go to Desmos to save time. Yeah, so this is 1,175 divided by 144 units long. And they go through the whole deal here. Next. I mean, this is a linear function. They're kind of switching it up on you here. I have y in terms of x. They also give you an interval on the x-axis, so I could just integrate this down with respect to x. I don't understand why they ask us to calculate the arc length of the graph of x equals g of y. So like solve for x, get x in terms of y, and then integrate with respect to y. All right, so I guess I'll show you both again here, just to remind you that, remember that very first example in this video, it said you can set up the integral with respect to x or with respect to y, and you should end up with, the same result. All right. So the curve they're giving us is, y in terms of x is f of x equals y equals, you know, 1/4 x. It was x over 4 minus 1. So just some linear function. And we're on the interval from x equals 2 to x equals 5, they said. All right. So yeah, just a straight line, just a straight segment. So from x equals 2 to x equals 5. Now when x is 2, it's a half minus 1, that'd be negative half for the y coordinate. And when x equals 5, 5/4 minus 4/4 would be 1/4. Right? So positive 1/4 for the y coordinate at 5. And this is just a straight segment, right? This is perfectly straight. So what's this arc length here? Well, again, S, right, little s. So as I was showing you before, right, if it's a straight segment, you can just break it up into horizontal and vertical components, make a big right triangle. This leg has a length of 3. Then this leg here, the vertical leg, you're going from negative 2/4, right, negative 1/2, negative 2/4 to 1/4. That's positive 3/4, right? That's a change of 3/4. So this arc length we're trying to find, right, is by the Pythagorean theorem, just the square root of 3 squared plus, 3/4 squared. And both of these would have 3 squared in common. I could pull that out and, square root of 3 squared is 3. So I'd have 3 times, and when I remove 3 squared from each of these, you got 1 plus 1/16. All right, because it'd be and the 3 squared's gone, it'd be just 1/16. And this is 3 times the square root of 17/16. But the square root of 16 is 4, so you can write this as 3/4 times the square root of 17, right? So there's the length of that piece of the line that we're drawing. 3 square root of 17 divided by 4. Well, if I'm doing arc length integrals though, I was given y in terms of x, I was given x values. So I'll say integrate from x equals 2 to 5 of the square root of, 1 plus, and y was in terms of x, right? So y prime squared, and that times the dx out here. If y is given in terms of x like this, right, 1/4 x minus 1, y prime would just be a quarter. So I plug that in here. Quarter squared is 1/16. So this is the square root of 17/16. Pull that out. That's the square root of 17, over 4, square root of 16, times the integral from 2 to 5 of just 1. This is a constant then. Now replace y prime with a quarter. And that would be 3 times the square root of 17, over 4, which is exactly what I got earlier just by looking at it as a big right triangle because you have a straight segment. Now, right, you could also set it up with respect to y, right? Now the x coordinates for this piece of curve are from 2 to 5. The y coordinates for this piece of curve are from negative 1/2, right, to positive 1/4. And if I took this here, right, y equals a quarter x minus 1, and I solved for x, right, you would add 1 and multiply everything by 4. That'd be 4y plus 4. X equals 4y plus 4. And then x prime, right, if I do dx with respect to y, dx dy, that would just be 4. All right, so, right, I could do the arc length is the integral from negative 1/2, right, y equals negative 1/2 to a quarter of the square root of 1 plus x prime squared. X prime squared, this would be 4 squared, so it'd be 16 dx. And this is just the square, oh, sorry, dy. These are y values with respect to y, right? And that's just the square root of 17, right? So I can pull that out. The integral from 1/2 sorry, negative 1/2 to 1/4 of just 1 dy. And that would just be y. And then you do 1/4 minus negative half. 1/4 minus negative half would be 1/4 plus a half. 1/4 plus 2/4, that's 3/4. 3/4 times the square root of 17. Right, so either way you do it, we get 3/4 times the square root of 17 units. Right, so the arc length 3 times the square root of 17. Get out of there, then all that, divided by 4, 3/4 of the square root of 17. Great. All right, so the first one objective is complete now, where I think we're given, x in terms of y, right? They want g of y. So now the other one I need to finish up with this arc length where I have y in terms of x, f of x. So yeah, here we're given y equals, f of x equals 2 times x to the 3/2 power. And we're over the interval from, x equals 0 to x equals 3. All right, so like I said, you don't need to really draw these curves to find their length. So I'm just going to go, you can look at previous examples if you wish, but I'm just going to go straight to the arc length integral without drawing the curve. Okay. So we're given this curve, right? Y is a function of x, 2 times x to the 3/2 power on the interval, right, from x equals 0 to x equals 3. So the arc y prime I'm going to need, right? Remember the arc length will involve y prime squared. Power rule here, this would be 3 times x to the half, right? You multiply by the power, subtract 1 from the power. Okay, so the arc length, s, it's going to be the integral from, x equals 0 to 3 of the square root of 1 plus our y prime squared, right? 3x to the half squared, and then times the dx out here. Now simplifying this, right? This would be the integral x equals 0 to 3, the square root of 1 plus, and then when I square 3, it's 9, and when I square x to the half, that would just be x to the first. So 1 plus 9x dx, right? Now, because this is a linear inside the square root, that's cool, but you could make a u substitution here. So just to practice that, usually expressions inside other expressions, you're trying to make things look a little prettier when you're doing substitutions. So I'd rather have the square root of a single variable than the square root of some big expression with 2 terms. So if I do a u substitution, let's say I let u be this 1 plus 9x here, right, then the differential of u, right, du, would be the derivative of this 9 with respect to x times the differential of x, right, remember. And so, dx, right, if I want to replace dx in the integral with something, I want to go from x variables to u variables, right? I want to write the integral in terms of this new u. So we're going to replace dx with 1/9 du, right? Just take the previous line here, divide by 9. All right, so I make all these replacements, and not only that, right, with definite integrals, you can also do the limits of integration, redo those. So the original lower limit, all right, so let's do lower first. The original lower limit was, x equals 0. Well, if I go into that substitution I made, u equals 1 plus 9 times 0, we're getting u equals 1 for the new lower limit. And then the upper limit. The original upper limit was x equals 3. And if I go into my substitution, right, u equals 1 plus 9x, 1 plus 9 times 3, we're getting u equals 28, 27 plus 1. So I'll make all these substitutions. So after substituting, this integral is the same as the integral from u equals 1, 28. Right? The new lower limit was 1, the new upper limit was 28. And then instead of the square root of 1 plus 9x, now I have the square root of u. I'm going to write that as u to the half, right, to make the integration easier. And then this dx is du over 9, or times 1/9. And because that's a constant multiple, I'll pull that out, right? So dx here replaced by 1/9 du, right? There's 1/9 du. Great. Now this is again, u is a dummy variable. This could be x dx, y dy, z dz. You treat this like anything else. So this is going to be 1/9 times, and then I can anti-differentiate this with respect to u, right? This would be u to the 3/2, right, times 2/3. We're going from u equals 1 to 28. I can pull the 2/3 out of this, make this 2/27. And then we're just doing u to the 3/2 from 1 to 28. All right, let's put this here, right? So this would be 2/27 times, and then 28 to the 3/2 power minus 1 to the 3/2 power. But 1 to any power is, so this is 28 to the 3/2 power minus 1. Here we go. This is how long that curve is. 2/27 times the quantity, 28 to the 3/2 power minus 1. That's what I'll be entering here. So 2/27 times the quantity, 28 raised to the 3/2 power, and then get down from there, minus 1 after, and close the quantity there. This should be good. Great. Yeah, so they actually go through, if you look at 28 to the 1.5 power, that's 28 to the first times 28 to the half. So that'd be 28 times the square root of 28. And you can rewrite the square root of 28 as 2 times the square root of 7. And then they go through and distribute the 2/27 and they get this thing, right? So like my answer doesn't look like their answer, but it is exactly the same value. Wonderful. So once again, exact answer, right? So we should be setting up an integral that we can take. F of x equals 6th of x cubed plus 9 plus 1/2 x to the negative first, or 1/2x. And we're going over the interval from x equals 1 to x equals 4. So again, I'm not going to draw the curve. All right, you can look at Desmos, see what the curve looks like. I'm just going to set up the arc length integral now to save some time. So we're given this curve, right? Y equals, now it was x cubed over 6, right? So 1/6 x cubed plus 9. And then the last term was 1 divided by 2x. That's the same as 1/2 times x to the negative first. Right? I'm just writing them like this so that the derivative will be easier. And we're on the interval from x equals 1 to x equals 4. Find the arc length. Remember, for arc length here, I need y prime. We're going to do it in terms of x with respect to x. Now, y prime would be 1/2 x squared plus 0, and then minus 1/2 x to the negative second. Okay. So my arc length, S, is going to be the integral from x equals, 1 to 4 of the square root of 1 plus, y was in terms of x, right? And y prime squared. So this half x squared minus half x to the negative 2 squared, and then times the dx out here, right? All right. This is very similar looking to a problem we saw a few examples ago. This expression here, when I square it, it's going to be 1/4 x to the 4th. Let's square that first term. when I multiply the two terms, you get negative a quarter x to the 0. So minus a quarter, but then you'll have two of those. So minus 2/4 or minus 1/2. And then multiply the last term with itself, plus a quarter x to the negative fourth. Right? And then when you add the 1, right, this is this expression squared. And then when I add this 1 on here, right, we're getting the following. We'd have a quarter x to the fourth, and then 1 minus a half is plus a half. Plus 1/4 x to the negative fourth. And do you see how this expression is exactly the same as this one, but with a minus a half and a plus a half instead of a minus a half? So like this expression I'm pointing at here, right, I got from squaring this with the minus in the middle. So I'd get this expression here by squaring this here with a plus in the middle. All right, so this here is equal to 1/2 x squared plus a half x to the negative second. That quantity squared. And we're taking the square root of this. So that square will go away. So I end up with the integral from 1 to 4. Integral from 1 to 4 of, the square root of this squared will just give me this. So the expression I'm left with here is half x squared plus, half x to the negative second, and then times your dx. Okay, now I know based on previous experience now that this is going to be a rational number, right? The limits are rational, coefficients are rational, my powers are going to be nice integers. No fraction powers or anything, so because this is going to be rational, I'm just going to enter this to save time. You should be able to do this yourself though, right? By hand, but I'm going to save some time here and just enter this into my calculator into Desmos here. So very similar to this actually, right? This is from few examples ago. So we're integrating from 1 to 4, okay? And then I had x squared, half x squared, so x squared over 2 plus half x to the negative second. And then, dx, right, with respect to x. Right? Say 87/8. Right, so this ends up being 87/8 when totally simplified, units long. All right, so let's enter this. 87 divided by 8 units long. Great. And moving on. Looks like probably just one more question here with arc length, and then we'll move on to surface area of a surface of revolution. All right, so here's one where they just ask us to round to 4 decimal places. So like back in the very first example. So we're given just y equals x squared. What's the length of that arc? What's the length of that curve just from when x equals 2 to x equals 6? Right, so again, I'll set up the integral and go to a calculator and round it to 4 decimal places. So yeah, y is given as a function of x, right? So, and then we're on some interval from x equals 2 to 6. And if I'm doing the arc length integral, right, I need y prime. It should be 2x, right? So the arc length, s, maybe the integral from x equals 2 to 6 of the square root of 1 plus y prime squared, right? So 2x squared, and then times your dx out here. Right? So that's the integral from 2 to 6 of the square root of 1 plus 4x squared, right? 2x times 2x, and then times dx. And this is approximately, right? They want us to just simply enter this, right? There's really nothing we can do to evaluate that at the moment by hand. There's methods in the future we'll learn. So I'm just going to change this integrand here to the square root of 1 plus 4x squared. And the limits of integration, right, were from 2 to 6. So changing those from 2 to 6. So approximately 32.2729, and the fifth decimal place is 4, which is less than 5, so I keep the fourth decimal place the way it is. I don't bump it up. So 2729 units long. 32.2729, and that's what I'll enter here. Right, approximately 32.2729. And then check it out. Great. Okay, so that's it for the arc length portion of this assignment. The other portion is on areas of a surface of revolution. So we're going to take these curves that we're drawing now, right, and rotate them or revolve them around a line, around either the x-axis or the y-axis. And if you do that, you'll create a surface, like kind of a sheet rolled up. Like if you imagine a sheet of paper rolled up, that creates a surface. I'll show you what I mean when I get to the next example. Okay, so we're asked now to find the surface area of a surface of revolution, when rotating around the x-axis, and I'm sure the other objective is around the y-axis, right? See, oh, it's just with a function g of y, but there may be some of these where we're rotating around the y-axis in that other objective, though I have a feeling. All right. So here, let f of x equals, so we're given y as a function of x over this interval. So again, we're just gonna, I'll actually draw this one. Right? That's some piece of a curve. And we're asked to use a calculator again because you'll see the integral we set up here, probably not very doable using u substitution alone. So we'll have to just type it in and approximate it to 4 decimal places. Find the surface area of the surface generated by revolving the graph of f around the x-axis. Okay, so let's see, I'll draw this to the best of my abilities. Maybe I'll pull it up in Desmos to make a better picture. We're given f of x or y equals, right, same thing as y, 2 times the square root of 16 minus x squared. And then we're over the interval x equals -1 to x equals 3, right? Just that interval. All right, so I'll draw this now. This would be the same as y divided by 2 equals the square root of 16 minus x squared. And then if I squared both sides and then added x squared, you'd have x squared plus y squared over 4 equals 16, right? So this is an ellipse centered at the origin. You may recall from maybe like a pre-calculus class, right? We're just looking at part of this ellipse, right? Not the entire ellipse. Just the part of it that's from x equals -1 to x equals 3. And also the part of it that has positive y coordinates, right? This is 2 times the positive square root. So also the part of it that, because there'd be a part, it's an ellipse, it's like an oval shape, right? Centered at the origin would be in the middle. And you'd have, 4, 4, 0. Like you could draw the whole ellipse, I hope, right? Based on your pre-calculus experience, algebra experience. There's a part above this and a part of the ellipse below this interval. Again, we're only concerned with the part where the y coordinate is a positive. All right, so just this piece of it here. So I'm just going to do this. We got, here's 0, 4, 0, 0, 2. 0, 2. 0, 2 would be on this ellipse. We'd have some point here at -1, and then, the top of the ellipse there, and then it starts coming down again there. There's the point above 3. Here's the point above -1. Just this piece of curve right here. That's it. There's our curve. There's our y equals f of x, right, over the interval that we were given. Now I'm asked to then rotate this around the x-axis. Right, so rotate this curve. Now remember I said it's going to create a surface, right? Imagine taking a piece of paper and I rotate it around some invisible line above it, wrap it around, right? And what happens is you create a surface, right? There's nothing inside, right? It's totally hollow. You can see my pinky down there. Totally hollow. You create this surface. Right? What's the area of this surface? The amount of space that takes up. So no volume, right? There's nothing inside. It's totally hollow. So yeah, I'll draw a rough picture as to what this surface would look like, right? So if I rotate that curve, I create, what's called a surface of revolution, right? Because I'm revolving some curve around some line. And the surface created would, go on top and then reflect it across, right? Like that on bottom. And then it's just like a rolled up piece of sheet, right? A rolled up sheet, right? Like this and back there, right? And all these little, again, I'm not the greatest artist in the world, I'm sorry, but it would be like this hollowed out barrel. And through the hole, right? The middle of it has nothing in it. There's no volume. It's just totally empty. We're just looking at the sheet rolled up. And in the middle of it is the line we rotated around, the x-axis. So again, it's almost like an empty barrel with no top and no bottom, right? It's like it's like around the surface around a barrel. All right. So you recall hopefully from earlier that when I was trying to find arc length, so here I would go to say some x value between -1 and 3, correspond to this point here, and I'd take a piece of the arc. Right? So there's some little, it's almost, again, if we're close enough, it's basically straight. And remember that little piece of arc was called ds, right? We said it had a length of ds, change in arc length, ds. If I wrap ds, right, if I revolve around the x-axis or revolve about x-axis, what you're going to create is a shape like this. Oops. Where this is your surface, right? Again, wrapped around. And there's a big hole in it, right? There's nothing inside it. There's no volume. This is actually called a frustum or frustum. I've never actually heard it said. So I'll just say frustum because I like that. All right, frustum or frustum. It's basically like a cone, surface of a cone with the pointy part lobbed off. So so again, this like thickness of it is ds, right? This edge here, which is like the thickness of the or the width of the little sheet wrapped up. And then you have a radius. So from this point in the middle of our curve here, the middle of ds, you have this radius. I'll call it r for, radius. And if you were to unroll this, if you were to take this sheet, this little thin sheet, and unroll it, it would pretty much look like a big long rectangle, especially if that's thin enough, right? If you get it really thin enough, it's basically a thin long rectangle. This isn't a proof or anything, all right? So please be aware that there are much more rigorous arguments for why the area of this is what it is. All right, but the area, all right, the area of these frustums or frustums, it's just that little piece of arc length. All right, how long is that? That's like the width of the rectangle. If again, if I unroll this, the ds would be like the width of the rectangle. And then if I fully unroll it, the length of the rectangle is going to be the circumference of our circle. All right, so times 2 pi r. And we'll be adding these up. Right, we'll take all these areas of the frustums and we'll do that for every single x value from -1 to 3. and that'll give us, all these, all this barrel shape down here is made up of a bunch of thin frustums, right? Frustum there, frustum there, frustum there, right? And add them all up, and you get the total area of that barrel surface, right? That surface of revolution. So our surface area, here's our surface area integral. And I'll actually take this to the next page as well. Now for surface area, so I don't have to keep writing out surface area, I'm going to call it capital A for area. It's just going to be adding up, right, integral, adding up all these frustum areas. 2 pi r times ds. Or again, r is the radius of the rotation, right, the radius of our circle. And to do the radius, that's just the distance from the line to the curve, right? On the picture here, this distance here would be r, right? From the line you're rotating around to the curve is your radius. So I'll take this to the next page because remember, I want to, ds is not necessarily horizontal, but it does have a horizontal and vertical component, right? You saw that in the first half of this assignment. So recall that ds, the little piece of arc, if I broke it up into its horizontal component dx and vertical component dy, ds was the square root of dx squared plus dy squared, right? We saw this again earlier in the video when talking about arc length, which I could then break up into two parts. I could write this in two equivalent different ways. Where I factored out dx squared, right? So, and then you had the square root of 1 plus y prime squared, right? Remember this, again, I did this already before, times dx, or, right, over here, or if I factored out dy squared, right, you'd have the square root of 1 plus x prime, right, where x is a function of y. 1 plus x prime squared times dy. Remember this? Hope you remember this, right? I don't know why I ask questions through the video you can't answer. So we're putting both of these in here. So we get two versions of this surface area integral again. All right, so area. 1, if you integrate with respect to x, the area is going to be the integral from, some x value, say x equals a, to x equals b. For our purposes, for our example here, that's going to be from -1 to 3 of, 2 pi r times ds, right? It was 2 pi r ds. And if I'm integrating with respect to x, ds, I'm going to write this way, where y is a function of x. So times the square root 1 plus, y prime squared, and then times your dx out here. Notice how very, very similar this is to our arc length formula. It's just the arc length, right? This square root of 1 plus y prime squared dx, that came from arc length. And then just take that little piece of arc, right? Take your arc and how far did it go around when you wrapped it around the x-axis or the y-axis? That's the circumference here. So it's your arc length times circumference. And now the only thing I would have to worry about now is I need to get r in terms of x. All right, so if I'm integrating with respect to x, I need to get r in terms of x, right? Write out r as some function of x. And then I'll be golden. Or, right, we can set up the integral for the surface area created, right, by rotating some curve around an axis. I could do it with respect to y as well. And you should be able to set up both. Right? For a lot of these, you could set up both. And they'll give you two different integrals. They might look similar, but they should end up giving you the same value though. So this is with respect to y. So I'd be the surface area of revolution, right? The area of the surface of revolution is some integral from y equals say some value c, so y equals d of, and then, again, it's the circumference of rotation, right? 2 pi r, the circumference of revolution, times the square root, and then this is your ds, right? 2 pi r ds. I'm writing ds this way with the dy and x prime, 1 plus x prime squared, and then times dy. And again, the only issue here would be that I have to get the radius, right? This radius here, I have to get this r. I have to get that now in terms of y if I'm doing integrals with respect to y, right? So get r in terms of y. There you go. I'm going to put this in a box here. There's your surface area integrals, right, for surfaces of revolution only, really. Okay, so it's arc length times circumference, right? Arc length times circumference, 2 pi r. And that's all that changes. It's your old arc length integral from the first half of this video, and then times 2 pi r times circumference. I know I said that already. So let's go back to our example and find what would be the surface area of this barrel shape, right? This empty barrel, no top or no bottom, right? It's this rolled up piece of paper. So, because I was given y as a function of x and values on the x-axis, I'm going to integrate with respect to x, right? So the surface area, once again, if I'm integrating with respect to x, that'll be the integral from x equals, for the points on this curve that I'm going to wrap around, we're going to do this for every x value from -1 to +3. Again, you got the 2 pi r, and we'll have to determine what r is in terms of x, right, times the square root of 1 plus, now if I'm doing in terms of x, right, y is a function of x this time, so we got y prime here squared, and then, times your dx on the outside. Okay. Now in terms of x, do you see how r, right, the radius of the rotation make any of these frustums or frustumes? Again, it's just the distance from the line you're rotating around to the curve, which here, that would be the y coordinate of my point on the curve. All right, that distance is just whatever the y coordinate is. So the radius is y, but I don't want the radius in terms of y. I want it in terms of x. Well, on this curve, y coordinates are this when it comes to x, right? So 2 times the square root of 16 minus x squared. That's the radius of the rotation, the radius of the circle produced by the rotation. So that's going to go in for r, right? This 2 times the square root of 16 minus x squared. And now it also need to get y prime. Y prime is going in here. Right, so we had y, so r is just, the y coordinate from the x to the curve. That was 2 times the square root of 16 minus x squared. And we have y equals, now I'm going to write it this way, 2 times 16 minus x squared to the half, because I need to take the derivative of this, and I like it better with the powers. Remember, you got to do power rule and chain rule, because there's something inside the power. So half of 2 is 1, so that's 16 minus x squared to the negative half, right? Then subtract 1 from the power, then multiplied by the derivative of the thing inside, right? Chain rule, which would be negative 2x. Okay. Now, if you'd like, I can write this as negative 2x would be in the numerator, right? And then 16 minus x squared to the negative half would be 1 over the square root of 16 minus x squared. So there's y prime. And that's going to go in here and be squared. All right, so let's substitute all this stuff now. So the surface area, or the area of that barrel created by rotating the curve around the x-axis, will be the integral from -1 to 3 of 2 pi, right, times the radius. And this is the circumference of rotation. And the radius in terms of x we saw for any x value for any of those frustums or frustums was this in terms of x, 2 times the square root of 16 minus x squared. So it's 2 pi r times the square root of 1 plus, and then y prime, right? Here's y prime in terms of x, negative 2x over the square root of 16 minus x squared. That's squared. Right? That is squared. And then times your dx out here. Okay. Now, honestly, they only want the thing rounded to 4 decimal places, right? They don't ask for an exact value. So I could seriously just enter this into my calculator and have it round, round it to 4 decimal places. But I'm going to simplify this a little bit. Okay. So 2 pi times 2 is 4 pi. I'm going to pull that out. Okay, so you got 4 pi, that's a constant multiple, times the integral from negative 1 to 3. And then left over in here, you got the square root of 16 minus x squared times another square root. So I can actually put these together, multiply these together. Square root of a product of the square roots. And then 1 plus, and then when you square this, you'd have 4x squared in the numerator, right? Negative 2x times negative 2x. And then the square root in the denominator would be gone. And you got times your dx. Right? And now if I put these together, right, what's going to happen is I have the square root of this times that. You're going to be multiplying this by this, right? And so taking that and distributing that times 1, that times this. And so if I want to make this as simple as possible, we're getting the following, right? This is 4 pi times the integral from negative 1 to 3. And then square root times square root, it's going to be a big square root. And then 16 minus x squared times 1, right? That'd be 16 minus x squared. Plus, and then 16 minus x squared times 4x squared over 16 minus x squared, right? The 16 minus x squareds would cancel. It would just be plus 4x squared. That's it, and then times the x on the outside. And put these together, that's plus 3x squared, right? So I'm just going to type this in. This will be 16 plus 3x squared, all inside the square root there. Right, and I'm done. Right, so I'll just enter this and round to 4 decimal places. So we have 4 pi. Again, you can just type pi and pi will come up, times the integral from negative 1 to 3 of, and I ended up simplifying that down to the square root of 16 plus 3x squared, right? All inside the square root there, and then the dx on the outside. Right, so this rounds to approximately 237.9605 are the first 4 decimal places. Then the fifth one is higher, is 5 or greater, it's 7. So I bump up the fourth one by 1, right? So 9606. Right, and I've written that on my page, right? So about 237.9606. Now be careful. I know that in the homework they already have this written for you, but remember this is an area, right? It's the area of some sheet of paper rolled up into a barrel, right? An empty barrel. So this will be square units, right? This is square units, not just units. It's not length anymore. It's area, and it's not volume, right? There's nothing inside it, so it's not cubic units either. It's got to be square units. And you see that in the homework too, right? They have these square units in the homework. You just enter a number. And to 4 decimal places, we said that was 237.9606. Right? Square units. Wonderful. And again, they go through the surface area integral formula here. Again, they have f of x instead of r. They're putting that because, the distance from the x-axis to some curve above it would just be the y-coordinate, just f of x. Right? So that's why f of x instead of r. And you'll see when they wrap around the y-axis, it'll be g of y instead of r. But I like putting r and then determining what r is. Okay, moving on. So here's one where we're wrapping around the y-axis. So let g of y, now this is just a straight up line, a linear function, but it's not arc length though. All right, so if it were just an arc length problem, right, like in the first half of this video, that'd be real simple. But I am rotating this around the y-axis and creating a big surface, right, and finding the area of that surface. So I will set up the integral here. So g of y, or x, equals negative y plus 2. Find the surface area of the surface generated by revolving the graph of g of y around the y-axis, right, over the interval from y equals negative 4 to y equals negative 2. Right? Enter an exact answer. So this time I need to actually be able to integrate the thing. All right. So we're given g of y, and that's the same thing as x, equals negative y plus 2, or 2 minus y, negative y plus 2. And then we're on the interval from y equals, negative 4 to negative 2. So this is just a straight line picture, right? That's a straight segment. So from negative 4 to negative 2 on the y-axis. And when y is negative 2, x would be 4. So you have the point 4, negative 2 there. And when y is negative 4, this would be, 4 plus 2 is 6, right? So you got 6, negative 4 on the graph. And it's just this straight segment here, not perfectly straight. And we're wrapping this around, rotating this around, rolling it around, whatever the y-axis they're saying. Right, so the surface created here, right, I'm not going to draw it for all the examples, but the surface created here would look like this, that reflected across the y, and then it's kind of wrapped up, right? So like a lampshade. Right, right. Kind of like a lampshade. I have to think about certain kinds of lamps with nothing in it, right? It's just this sheet rolled up. There's nothing inside, no volume. That's the y-axis running right through the middle, y-axis. So when I'm doing frustums, I'd be picking some y value here, between negative 2 and 4. That'll take me to some point on the curve with a certain x value as well, from between 4 and 6. And I'd have this little piece of curve, we'll call it ds, right? And then it's going to wrap around, right? This little ds will wrap around the y-axis, and the radius of that, right, I'll call r, the radius of that rotation. Right? And then once again, the area of the surface created will be the integral of 2 pi r ds. And I rewrite ds in terms of stuff with dx or dy, and I rewrite r in terms of x or y, depending on what I want to integrate with respect to. Right. So the area of this surface, this lampshade, well, I was given everything in terms of y, right? So I'm going to get everything in terms of y. So we're going area equals, right? I'd be creating these little frustums or frustums for every y value from negative 4 to up to negative 2 of 2 times pi. Now, if I want to integrate with respect to r, right, look at this radius here, right? The radius of rotation, right? The distance from the line you're rotating around to the curve, that's your radius of rotation, or radius of revolution, whatever you want to call it. That is the x coordinate, right? I'm going left and right. So that's the x coordinate of this point. But I don't want it in terms of x, I want it in terms of y. And we saw from here earlier, the x coordinates on points on this curve are the opposite of the y coordinate plus 2. So negative y plus 2 is the radius. So 2 pi r, r is negative y plus 2 when we write it in terms of y. And then ds, right? ds is the square root of 1 plus, now if I have x in terms of y, right, we're going to have x prime in here squared. And what is x prime, right? X prime in terms of y would just be negative 1, right? It's a very simple linear equation, linear function. So negative 1 for x prime, but that's going to be squared. Make it nice and easy. And then times your dy, right, out here. All right. I should also be able to set this up in terms of x. I will show that to you with this example, just to let you know. You should be able to set up both sometimes. So sometimes it'll be tough, right? Depends on what the function looks like. Here I can solve for x, and I can also easily solve for y in terms of x. There'll be some functions, some curves out there where solving for y or solving for x may be impossible or very, very difficult. So you may not need to set up both there. I mean, you never really need to set up both, but very often you could. So let's just, oh, that's a little tangent there, sorry. Let's go through and finish this. So this, right, this is just the square root of 2, 1 plus 1. So I've got 2 pi times the square root of 2, that's all constant. So 2 pi times the square root of 2, and I'll pull outside. And then we'll have the integral from y equals -4 to -2. And all that's left over is this linear function in here, -y plus 2, that radius. And this should be relatively easy. This would be 2 times pi times the square root of 2 times, and then this is your -1/2 y squared plus 2y. Sorry, brackets. And then we're going from y equals -4 up to y equals -2. Right, so I plug in -2, plug in -4, and subtract them. So this is 2 pi times the square root of 2. And then when I plug in -2 for y, this would be 4 times -1/2, that would be -2, plus -4, be -6. All right, when I plug in -2 for y. And then when I plug in -4 for y, that'd be 16 over 2, this would be -8, plus, and then -8, that'd be -16. All right, -16. And, -6 minus -16 would be plus 16, right? So that's 10. That's all 10 here, and 2 pi times square root of 2. 2 times 10 is 20. So this ends up being 20 pi times the square root of 2. And again, this is an area, right? This is the area of this lampshade, this rolled up piece of paper. So it's square units, right, for surface area. So 20 pi times the square root of 2 square units. So that's what I'm going to enter back on the assignment. And then I'm going to also go through and show you, you could have set up the integral with respect to x. So we got 20 pi times the square root of 2. You can also set up the integral with respect to x and find it that way. Right, so let me do that. So this is correct, great. Let me go back to the paper here and take this same surface and set up the integral with respect to x instead. All right, so we got 2 pi r ds, right? And I'm going to write things in terms of x now. All right, so if I'm in terms of x, right, now the interval, instead of being from -4 to -2, right, those are the y coordinates of this piece of curve that I'm rotating around the y-axis. The x coordinates for all the points on this piece of curve are from 4 to 6, right? So my new limits of integration are going to be from 4 to 6. So the area equals the integral from x equals 4 to 6 of 2 pi r, and I want r in terms of x. Remember, I'm rotating around the y-axis, so that r is just x, right? We saw that. The radius is just the x coordinate of the point on my curve. So it's 2 pi x, simple as that. And then I need to solve, we had x equals -y plus 2 earlier. Solve this for y. Y would just be -x plus 2. Right, just add y, subtract x. And then there's y in terms of x, and y prime would be -1. So now here's 2 pi r, and then ds would be the square root of 1 plus y prime squared, right? Y prime in terms of x is just -1 squared. And then times dx, right, here with respect to x now. All right, let's see what happens. Well, this here, the 1 plus y prime squared, this is just the square root of 2 again. And I've got 2 pi times the square root of 2. I can just pull that out. 2 pi square root of 2. And then I'm left with the integral from 4 to 6. And when I pull out the square root of 2 and pull out the 2 pi, all I'm left with in there is x, right? So this is 2 pi times the square root of 2, and then times half x squared. And we're going from 4 to 6. And I could pull the half out, like this pi times the square root of 2 times, just x squared from 4 to 6. And that'd be pi times the square root of 2. And when I plug in 6, that's 36. When I plug in 4, that's 16. 36 minus 16 is 20. And this is exactly what I got earlier. All right, exactly. So it just goes to show you that sometimes, again, if the functions are nice looking, right, you can integrate with respect to y, you can set up the integral with respect to x, and you'll get the exact same surface, right? Both of those represent the surface of this lampshade that I created by rotating that curve around the y-axis. Great. Oh, and I think they actually have you doing it here. So there's the curve. Do they have you actually rotating it around? Yeah, so look. Oh, this is nice. So I didn't do this in the last example, sorry. But they have after you answer the thing, they have it in the answer explanations. See this picture of the curve here, just from y equals negative 4 to 2, just this little piece, they have you rotate that around. You see the lampshade created? Ooh. All right, I can move this graph. Here, you can see the shade. You see that lampshade? All right, that surface created? That's what we found the surface area of. All right, very nice. All right, so yeah, again, I said, sorry if I missed that in the last answer explanation. All right, so let's do this again. All right, this time I'm not going to set up both integrals, right? I just wanted to point out last example that you could sometimes, but you don't have to, right? If you set it up with respect to x or with respect to y, that should be enough, right? All right, so we get g of y or x equals the quantity y plus 1 squared. Here I'm just setting up the integral and using a calculator and rounding to 4 decimal places. Right, so I'll set up the integral to find the area of the surface created by rotating. And we're rotating around the y-axis from the values of y equals negative 2 to positive 1. So again, you don't need to draw the picture. I will though for this one, and then after this, I think I'm going to stop drawing the picture of the curve. But we're given g of y, right again, which is the same as x, is the quantity y plus 1, squared. X is a function of y. And we're on the interval from y equals, negative 2 to 1. So here's this piece of this curve. Now this should be some parabola with a vertex at the point 0, negative 1, and then opening to the right. Where we're going from negative 2, positive 1 here. And when y is negative 2, right, this would be negative, this is x equals 1. When y equals 1, x equals 4. Let's say a 4 or 1 on here. And like I said, it's part of a parabola. The vertex would be at actually 0, negative 1. When y is negative 1, x would be 0. And you got this piece of curve here. That's it. And we're rotating this right around the y-axis, they said. Okay, so let me just try to draw a very, very rough sketch of the surface created when we do this. We got this piece of curve here, right? It's like that, a little parabola piece, and then the y-axis, actually the y-axis is touching the curve, and rotate this around, reflect it around the y-axis, right? It should be touching, sorry, it should be touching the curve, and then like that. Oh, that's crappy. And then all circular, right? Do a little tornado up here, little tornado down here. All right. this surface with the y-axis going through the dead center here, right? Yeah, that's pretty. That we'll probably get a better looking picture, right? When we answer this and look at the answer explanation and do that rotation in the graph and in the computer. But yeah, so they gave me everything in terms of y, so I'm going to do this for y values, right? If I were to take any of the y coordinates, any of the y values from -2 to 1, go to some point on this curve, right? That'll also correspond to some x coordinate between 0 and 4. Um, take this little piece of curve here, call it ds, right? A little tiny piece of curve around that point. Rotate it around, you get those little frustums, right? So here's a frustum, and here's a frustum, and here's and then we're adding all these frustums up, to make the whole surface. Now the radius, right, of rotation is, once again, the distance from the line of rotation, the axis of rotation, to the curve. That is an x coordinate, right? If I'm going left to right, it's x. If I'm going up, down, it's y. The radius is the x coordinate of this point. Well, x coordinates on this point on this curve are the y coordinate plus 1 squared, right? So I can write the radius in terms of y, and I also would need x prime if I'm integrating with respect to y, right? So what's x prime in terms of y? That'd be 2 times the quantity y plus 1 to the first times 1, right? The derivative of the inside would just be 1. So just 2y plus 2. All right, distribute the 2 there. So x prime's 2y plus 2. I got the radius now, the radius of rotation in terms of y. So we can find our area. We can find the surface area of this tornado on top of tornado thing. Right, so the surface area, integral from, we're doing this for every value from y equals -2 to 1. Remember, it's the circumference of rotation, right? 2 pi r. So r was this y plus 1 quantity squared times ds, right? And ds, when I write it with respect to y with the dy on the outside, that's the square root of 1 plus, x prime in terms of y, right? Squared, 2y plus 2 squared, and then times your dy out here. And you know what? I'm just going to enter this. Okay, that's all they want is enter this and round to 4 decimal places. All right, so big expression in here. So back on the calculator, the Desmos site, enter a new integral. I'll pull the 2 pi out. All right, so 2 pi times the integral going from y equals -2 up to y equals 1. And you had the quantity y plus 1 squared times the square root. And then inside that square root was 1 plus the quantity 2y plus 2, right? That was your x prime squared. And then outside all this, right, times dy. All right, so this is the surface area of those tornado shapes, right, is about 57.0356. But notice the fifth decimal place is 5 or above. So I bump up the fourth decimal place by 1. So 0.0357. So approximately 57.0357. And don't forget that will be square units. All right, sorry, I wrote that out here. 53.0357 square units is the surface area of this shape. All right, well, the area of the surface created by rotating that curve around the y-axis. All right, so I'm going to enter that in my assignment. 57.0357 and submit. Again, you can look at the answer explanation. All right, once again, looks like, so here's the curve. Look at it this way. So you got your x-axis, y-axis. Here's this parabola, right? We're only looking at between -2 and 1, though, on the y-axis, right? Y equals -2 to y equals 1. So just this little piece here. Revolve it around the y-axis, and you see the tornado shapes being created, right? Little tornado up there, tornado down there, right? And we just found the area of all that surface. about 57.0370357 square units. Right? Wonderful. So this time, right, they just want us to set up the integral. Right, what are the limits of integration and what's the integrand? And that's it. Okay, so now I'm going to stop drawing the curves, right? We're going to see them in the answer explanations. So I'm going to stop drawing the curves and just set up the integrals, find the surface areas. So this time the curve we're given is f of x equals or y equals the square root 5x minus 2, right? Which I'm going to write as 5x minus 2 to the half, right? Because remember, I need to take the derivative of this thing when I go into my surface area integral. And we're on the interval on the x-axis from x equals 4 to x equals 5. And we're rotating or revolving around the x-axis. So remember, if this is the x-axis and I take any point, any piece of curve here, let's take this, there's a little piece of curve, and I rotate around the x-axis, right? The radius of rotation is from the x-axis to the curve. That'd be the radius, which is the y coordinate of that point. Right? You're going up and down. But I want y in terms of x, and that's this here, right? So when I integrate with respect to x, I'm going to use this as the radius, 5x minus the square root of 5x minus 2. So once again, surface area, right at the basic integral again, integral of 2 pi r ds. But rewriting things in terms of x, we get the following. The integral from x equals, right, we're going from 4 to 5 of the circumference of rotation, 2 pi r, and I said a second ago, the radius here of the rotation in terms of x is the square root of 5x minus 2 times, and the square root, right, the ds is the square root of 1 plus y prime squared, right? So I'll put y prime in here squared and then times dx, right? Now I got y up here, right? We need y prime. That'd be 1 half times 5x minus 2 to the negative 1 half, and then times 5, right, for the chain rule. So that's 5 halves times 5x minus 2 to the negative 1 half, right? So I'm putting that in here, and they only wanted us to, you know what, just to save on some typing, let's simplify this a tad. Okay, so actually I'm going to write this as 5 over, and then 2 times the square root of 5x minus 2, right? Because that's 5x minus 2 to the negative 1 half, or it'd be 1 over. So 5 over 2 times the square root of 5x minus 2, right? And this is being squared. All right, now, so I do some simplifying here, right? This is the integral from 4 to 5 of 2 pi. You got the square root of 5x plus 2 here, or sorry, minus 2, times square root, and we can put these together, right? Square root times square root. Multiply these in a second. 1 plus, and then when this is squared, this y prime is squared, you have 25 in the numerator, and then 4 times the quantity 5x minus 2 in the denominator, right? And then times your dx out here. Okay, and now putting these square roots together, right, we're going to multiply this by this and distribute it, right, to each of those two terms. So this is integral from 4 to 5 of 2 pi, and then a big square root. 5x minus 2 times 1 is 5x minus 2. And then 5x minus 2 times the second term, the 5x minus 2's would cancel, you just have plus 25 fourths, okay? And then this is negative 8 fourths plus 25 fourths, so this in here is actually 5x, minus 8 fourths plus 20, plus 17 fourths. And I guess if you put these together, So it'll be 20x plus 17 all over 4. All right, multiply that by 4 over 4. Yeah. And then the square root of 4 is 2, and that'll cancel with this 2. So that'll be gone. So I'll be left with just the square root of 20x plus 17. Sorry about that. But we'll be left with this. Integral from 4 to 5 of just pi times the square root of 20x plus 17. Right. And they don't want an exact, this one I could actually do a u substitution for. I could get an exact answer out of this, but they do not want that. All they want is you to enter this integral, right? Enter the limits of integration. Now you could have done it up here too, right? You could have entered 4 or 5 and then all this, right? It wouldn't have been wrong. I just wanted to simplify it a bit so it would take less typing. So lower limit 4, x equals 4, upper limit x equals 5. And then my integrand here was pi, right? Ended up being just pi times the square root of 20x plus 17, all in the square root there. And that should be good. And yeah, that's actually what they had as well. So that totally simplified it. But then if you entered the big crazy expression earlier, right, as long as it's equal to the final result, they should give it to you. Okay, and let's look at this, right? So here's the curve in question. Let's actually move this graph a bit so we can look at it. Right, so there we go, right? So here's the curve, and we're looking at it just between x equals 4 and 5, so just this little piece here. And I'm rotating around the x-axis, so you get this thing here, and let me just finish the rotation. And now you can see this little, again, it's kind of like one of them thin lamp shades again. All right, you're getting and we found the surface area. Well, we set up the integral that would find the surface area of that, and that's all they wanted. Okay. So this time they actually want us to find the exact surface area, right? So the integral we set up should be doable. Right. And this is one of them straight line ones again, right? Y equals 4x minus 1. That's a linear function. I'll be taking some segment, some straight segment, and rotating it around the y-axis between y equals 1 and 3. All right, so once again, I am not going to draw the curve, even though it wouldn't take that long. What the heck, it's only a straight line. I'll draw the curve. It's straight. Yeah, I know what it looks like. So yeah, we are given this function, right? F of x equals, or y equals, right? 4x minus 1. And we're on the interval on the y-axis, though. Right? They give us y values. Y is between 1 and 3. And we're going around, we're taking this piece of curve and we're rotating it around the y-axis, right? And find the volume of the surface created. So if I draw this, y equals 1 to y equals 3. Now when y is 1, if I could take this here, solve for x, right? X would be, y plus 1 multiplied by a quarter, right? So a quarter y plus a quarter. If you solve for x, right? You should be able to go back and forth between these. And there's a function of y. You could call that g of y if you want. Yeah, so when y equals 1, you got x equals a half. Right? It'd be a quarter plus a quarter, 2 quarters, a half. And when y equals 3, you got 3 quarters plus 1 quarter is 4 quarters. That's 1. So you got the point 1, 3. You got the point 1 half 1. It's a straight segment, right? Linear function. Then we're rotating around the y-axis. All right, so can you see that this would create another lampshade looking thing? All right, the surface created again would be this, look like this. You got this over here, and then connected by some circles, right? All these festoons that make it up. Yeah, you'd get some lampshade looking thing again. What's the area of this? Now the radius, right? The radius is the distance from the rotation, right, to the surface, right? On here, that would be this distance here. Right? So if I pick some y coordinate here, that'll correspond to some x-coordinate as well. The radius, though, is the distance from the curve, the line you're rotating around to the curve, which would be the x-coordinate of that point. But I want the x-coordinate. Now, let's set this up both ways. Honestly, I think it would be easier to set it up in terms of x. All right, I'll show you both integrals. All right, we'll see which one we like better. But the x-coordinate of any point on this curve is a quarter y plus a quarter, right? Or a quarter of y plus 1, whatever. So if I set this up, if I want the area of this lampshade, I want the area of this surface. Let's do it with respect to x. I'll do WRT with respect to y. Let's start with y. Sorry, y, because they gave me y coordinates, right? Y values. So this will be the integral from y equals 1 to 3 of, the circumference of rotation, 2 pi r. But r in terms of y was this, quarter y plus a quarter times ds, right? And ds is here the square root, and I want it with the dy at the end, right? That'll be 1 plus x prime. So I solve for x here. I got x in terms of y, right? So x prime would just be a quarter. Nice constant. So there's x prime squared. Okay, so a lot of constants I can pull out here. This is 1 and 1/16. So 16/16 plus 1/16. This is 17/16 in here, but when I'm taking the square root, right, that'd be the square root of 17, divided by 4. And then this here, I can pull a quarter out, and that'd be a quarter times y plus 1. And, the 2 here and a quarter make a half. And then half of the square root of 17 over 4 would be an eighth of the square root of 17, right? Square root of 17 over 8. So I'm going to pull that constant out. Oh, yeah, sorry. I said I'd set up both integrals and see which one we like better. Well, I'm just doing this one. All right. I'll set up the other one too. Why not? So we got the square root of 17 over 8, all right, times the integral from y equals 1 to 3. And when I remove all this junk, right, the half, the 2, the square root of 17 over 4, I'm left with pi. All right, I'll pull pi out as well as a constant. What I'm left with is just y plus 1. That is all. All right, just y plus 1. And so we get the square root of 17 over 8, and then times, half y squared plus y. And we're going from y equals 1 to 3. The square root of 17 over 8 times. When I plug in 3, that'd be 9 halves plus 3. 9 halves plus 6 halves is 15 halves. Minus, and when I plug in 1, half plus 1, that's 1.5, that's 3 halves. Well, 15 minus 3 is 12. 12 halves is 6, right? So this would be 6 root 17 over 8. And 6 over 8 reduces to 3/4. So it's 3/4 square root of 17, right? Or square units, right? That's the surface area. So 3 square root of 17 all over 4, or 3/4 square root of 17, whatever. All right, so I got it that way with respect to y. Let me show you that with respect to x, but you get the same thing. And I have a feeling it's going to be a better integral, a nicer looking. I mean, this wasn't terrible. Yeah, there were some fractions or whatever, but it wasn't terrible. With respect to x now, so I'm doing, the x interval for this piece of curve that we're rotating, right, is, y was 1 to 3, x is a half to 1. So I'm doing this for my limits of integration. We're going to integrate from a half to 1. And we were given y in terms of x earlier, so y prime in terms of x, that's just 4. Y equals 4x minus 1, y prime would be 4. So the surface area this time is integral from x equals 1/2 to 1 of the circumference 2 pi r. Remember, the radius is here, the distance from the y-axis to the curve, and that's just the x-coordinate. That's just x. Easy. Times the square root, right? And this is your ds, right? And I want the times dx here. And it's 1 plus y prime squared, right? 1 plus 4 squared. Well, that's just the square root of 17. So you got 2 times the square root of 17 times pi. I can pull all that out. So 2 pi square root of 17, right? Those are all constant factors. Integral from a half to 1, just x dx, right? And very easy integral. That'd be 2 pi times the square root of 17. And then we're doing half x squared, right? From 1 half to 1. I could pull the half out, make this pi times the square root of 17. And then we'll just do x squared from a half to 1. And when I plug in 1, I get 1. When I plug in a half, I get a quarter. 1 minus a quarter is 3/4, right? So this is 3/4 pi square root of 17. Oh, and I forgot the pi earlier, didn't I? I forgot to keep writing the pi. Pi there, pi there, pi there. So this should be 3/4 pi. So square root of 17 over 4. Sorry about that. And then again, square units, right? And it's the same thing, right? It doesn't matter, right? I've said this several times now with arc length and with surface area for areas of revolution. It doesn't matter if you set it up with respect to x or with respect to y, right? You'll get if as long as you're doing it properly, you'll get the same results each time. All right, so let's go back and enter that, right? That was our solution here. So we got 3 pi times the square root of 17 in the numerator, and then divided by, and then 4 in the denominator. There we go. And once again, in the answer explanation, they should have a nice little like where you can see here is my curve, right? Just this line between y equals 1 and 3, and then I rotate that around the y-axis and create this little lampshade, right? This lampshade surface. And we have just found the area of that surface is 3/4 pi times the square root of 17, square units. Okay. All right. So now they just want to set up the integral again. So this time, because it's not nice, I mean, it's a cubic. I could draw it, but I'm not going to draw it. I'm just going to set up the integral. And notice they have dy here, right? So I want things in terms of y. All right, so we're taking this piece of curve from between y equals 0 and y equals 2 and revolving it around the y-axis. So remember so we have g of y, again, which will just be the same as the x coordinate, right? G of y equals x is 4/5 y cubed or 4y cubed over 5. And we're on the interval from y going from 0 to 2. And we're going around the y-axis. So just don't forget, when you go around the y-axis, what the radius is like. Right? So again, if I took some piece of curve here, some little tiny thing, right, this is the y coordinate for that. It would have some x coordinate as well, right, down here somewhere. If I rotate that around, right, this is the radius here, right, the distance from what you rotate around to the curve. And that'll just be the x coordinate of my point. But on this curve, if I'm integrating with respect to y, I want everything in terms of y. The x coordinate of points on my curve are, we see x equals 4/5 y cubed, right? So I'm using 4/5 y cubed for the radius. All right, so rotating this region around the y-axis, surface area of that rotational surface, right, would be the integral from y equals 0 to 2 of, the circumference, right, 2 pi r, again, r in terms of y, 4/5 y cubed, times, and then ds, but with the dy at the end, right, dy pulled out, so that'd be the square root of 1 plus x prime squared, right? So this was x in terms of y, it's x prime, that'd be 12/5 y squared. So that's what I'm putting in here, 12/5 y squared. squared, so that's a 2. So there's x prime squared. I can simplify this a tad. This would be the integral from 0 to 2. All this out here, this would be 8 pi over 5. Right? 8/5 pi times the y cubed and times the square root of 1 plus. And then when I square 12/5 y squared, there'd be 144 y to the 4th, over 25. And really, if I make 1 25 over 25, you can divide by the square root of 25, right? The square root of 25 is 5. That would put another 5 in the denominator here. I could actually make this integral from 0 to 2 of 8 pi over 25, right? Because again, make this 25 over 25, right? And then you have all over 25. Do the square root of 25 is 5. Pull that out. Right, so 8 pi over 25 times y cubed, and then times the square root of 25 plus 144 y to the 4th, right? And then your dy outside, right? Times dy. So I'm going to enter this. I mean, you could enter the original thing, right? All they want is some expression equivalent to the correct answer. But we're setting up this integral, right, to find the volume, sorry, not the volume, the area of the surface generated by rotating a curve around the y-axis. So y equals 0 to y equals 2, right, putting in the limits. And then inside, right, the integrand was 8 pi, right, 8 pi over 25 times y cubed times the square root, and inside the square root, 25 plus 144 y to the 4th. Now you may see it that this is actually something we could integrate with a nice u substitution, but they don't want that, right? They just want us to set up the integral that would give us that surface area. They wrote it out with the fractions and whatnot, but whatever, okay. All right, and then again, here's what it would look like, right? Here's the curve we're looking at, between y equals 0, y equals 2. Rotate this around the y-axis, and it creates this like tornado-looking shape, right? It's tornado surface, and we found the integral anyway, right? That would help us determine the volume, the surface area of that tornado, not volume, right? There's nothing inside. So it looks like the rest of these are going to be on this objective where it's rotating around the x-axis, right? So we've seen a couple around the y-axis. We've seen one example, I think, where we're going around the x-axis. The rest of them will be around the x-axis. Right? So just like I said earlier, for a bunch of these now, I'm going to stop drawing the curve. All right, we're just going to set up the integral. All right, so this time I'm given the curve f of x, right, which is y, equals the square root of 3x, right? The square root of 3x, or you could think of this as 3x to the half, same thing. On the interval from x equals 0 to 1, right? So x is in the interval 0 to 1, and we're rotating around the x-axis. So again, real quick picture here. I'm not drawing the curve, I'm just saying, if you rotate a piece of curve, let's say there's a piece of curve there, x value for that piece of curve, y value for that little piece of curve. But if I rotate around, the radius of rotation is just the y coordinate, and that's the distance from the x-axis to the curve. But I want to integrate things with respect to x, I'm going to see in a second. So what is the y coordinate on our curve in terms of x? It's the square root of 3x, right? So I'm going to use square root of 3x for the radius. All right, so our surface area, right, the area created by rotating this curve around the y-axis, the area of that surface is going to be the integral from x equals 0 to 1 of the circumference of rotation, 2 pi r. So that's 2 pi times, the square root of 3x, right? I want in terms of x, or the integrating with respect to x, times, and then our ds, right? The one with the dx on the outside. And that's 1 plus y prime squared, right? So I need y prime. Y prime would be half 3x with a negative half, and then times 3, right? There's 3 inside. So that'd be, 3 halves times 3x to the negative half, which I could also write as 3 over 2 times the square root of 3x. That's going to go in and be squared, right? So when I square, I'll just write it right now. When I square this, I'll have 9 up here, and then in the denominator, you'll have 4 times 3x, so 12x. And really, that would reduce to 3 over 4x, right? 9 over 12 is 3/4. And then I have a square root times a square root, right? So I can take this 3x and multiply it by the one, get this all in the square root. The square root of a product is the product of the square roots here. Distribute the 3x. I'm going to pull the 2 pi out. We got the integral from x equals 0 to x equals 1 of the square root of 3x, right? 3x times 1, and then 3x times 9 over 12x, that'd be 27x over 12x. The x's would cancel. I have 27 twelfths, which would be 9/4. All right, 9 over 4 plus 9/4. Okay. And then, you got the dx on the outside. Right? And then here we have the square root of a linear. So I can do this with a u substitution again. Right? You saw there was an example about maybe an hour ago. This is 2.5 hours now. But I saw an example of an integral earlier in the video where we had the square root of a linear, and I could easily do that by doing some sort of u substitution. So I'm going to let u replace the expression inside here, 3x plus 9/4, right? And then du would just be 3, right? The derivative of this times dx. And so, if I were to replace the dx, right, dx would be 1/3 du, or du divided by 3. And then the limits, right, with definite integrals, right, when you make substitutions, you can, as long as everything's continuous, right, you can replace the limits. So the lower limit is now going to be u equals, and then, the original lower limit was 0. Plug that into my substitution. 3 times 0 plus 9/4 is just 9/4. All right, so the new lower limit will be 9/4, and then the upper limit, the original upper limit was 1. Replace x with 1 in my substitution. 3 plus 9/4. That's 12/4 plus 9/4. That'd be 21/4. Okay, 21/4. All right, so I'll make those my limits. Maybe I could have done, yeah, well, too late now. So let's make these substitutions. All right, so now I have 2 pi times the integral from, now everything's in u. I'm in the u world instead of the x world. When x was 0, right, we said u was 9/4, right? So lower limit 9/4. When x was 1, we said, 3 and 9/4, right? 5 1/4, 21/4 for the upper limit. And now instead of the square root of 3x plus 9/4, that's the square root of u. So I'm going to write it as u to the half. And then dx is being replaced by 1/3 du. And I'm going to pull that 1/3 outside. Okay, so now I have 2 pi over 3 outside, but there's the 1/3 du replacing the dx. And there, everything's replaced. Now I have this integral in terms of all u's instead of x's, right? We got rid of all the x's. And this is 2 pi over 3 times, and then this antiderivative would be, u to the 3 halves times 2/3, going from 9/4 up to 21/4, okay? And then I can pull the 2/3 out. make that 4 pi over 3, or sorry, 4 pi over 9, right, 2 times 2, 3 times 3. And then we're doing u to the 3 halves from 9 fourths, 21 fourths, okay. So we're getting 4 pi over 9 times 21 fourths to the 3 halves power minus 9 fourths to the 3 halves power. Okay. Now, notice how both of these have 1/4 to the 3 halves power. Off to the side here, 1/4 to the 3 halves, right? The square root of a fourth is a half, and then that cubed is 1/8. So both of these have a factor of 1/8, right? So I'm gonna pull that out. Now 4 pi over 8 is just pi over 2, so this would be pi over 18. Right? I'm factoring out an eighth. This times an eighth would be pi over 18. Right? Times, and then you just have 21, right? I pull out the 1 over 4 to the 3 halves. 21 to the 3 halves minus, and then 9 to the 3 halves would be left over here. But 9 to the 3 halves is nice because the square root of 9 is 3, and then 3 cubed is 27. Right? So minus 27. And there we go, right? That's much nicer looking. And I think they might also, they might write this as the square 21 times the square root of 21, right? They might write it that way because that's 21 to the 1.5, 21 to the first times 21 to the half. They might write that way as well, but I'm going to write it with the 3 halves power. And don't forget, this is, square units, right? This is a area of a surface generated by rotating some curve around the x-axis. Right. So we got pi over 18 times the quantity, 21 to the 3 halves power minus 27. Oops, make sure this in the power, minus 27 after close the parentheses. Square units. Wait. See, they wrote it as 21 times the square root of 21, and then distributed the pi over 18 to get this. So they are the same number, right? I said it was correct. Right. Right, once again, let's take a look at the curve. Right. So here's the curve, right? Just between x equals 0 and x equals 1. Right, yeah, 0 and 1. Rotated around the x-axis, you create kind of this bowl shape, right? It's like a little bowl, but hollow. There's nothing inside it, though. It's just a sheet, right? I know it looks solid, but it's not solid. And the surface area I created would be what we got here. They even wrote it a different way down here. But all these are the same value. Let's do it again. We're taking some curve from x equals 0 to 3, rotating it around the x-axis and finding the area of the surface produced, right? So once again, just setting up the integral and evaluating, and they want an exact answer again, so I should be able to evaluate the, do the integral that we set up. So here the curve is 1/5 x cubed, right? It's x cubed divided by 5. And then we're on the interval from, x equals 0 to 3. And we're going around the x-axis. All right, so remember, when you're going around the x-axis, the radius is a y-coordinate. From the x-axis to your point, that's a y-coordinate. But in terms of x, on that the x-axis to your curve, that's just 1/5 x cubed. So it's just a function we were given. We use that for the radius. And then the surface area produced, right, would be the integral. We'd be going from x equals 0 to 3 of, the circumference of rotation, 2 pi r. 2 pi times this 1/5 x cubed. And then times your ds, and I'm integrating with respect to x, so I want the one with dx out here. So it would be 1 plus y prime. This is y. So y prime, that would be 3/5 x squared. All right, and that's getting squared in here, so I'll just write out the result of that. When I square this, that'd be 9/25 x to the 4th. and then dx. Okay. All right, so something I'm saying, you got 2 pi, you got a fifth, so I can pull 2 pi over 5 out of this. And then integral from 0 to 3, you have x cubed. And then this expression in here I'm going to put together. This would be 25 plus 9x to the fourth all over 25, right? If I got a common denominator, this is 25 over 25. And then the square root of 25 is 5. Sorry. Square root of 25 is 5. I'll have another 5 as a factor in the denominator that I can pull out. So this would be 2 pi over 25 out here, right? 5 times 5 in the denominator. Integral from 0 to 3 of x cubed times the square root of 25 plus 9x to the fourth now, right? No fraction, because like I said, I already took the square root of 25 down here, pull out 1/5. Right. Now this integral I should be able to do no problem with a u substitution, right? See inside the square root there? The derivative of an x to the fourth polynomial is an x cubed polynomial, right? Degree 4, degree 3. So it would be a very good candidate for a u sub. So over here, I'll let u place this 25 plus 9x to the fourth. And then du, right, would be 36 x to the third dx. And do you see that there's an x to the third times dx here, right? An x to the third times dx here. So that x to the third times dx in the integral, when I change it to things with u, will be 1/36 du, right? Divide by 36. So I'm replacing this and this with 1/36 du, and then this inside the square root, right? Replacing that with u. And then all the x's will be replaced. And I'll do the limits as well. Do this up here. Right, the limits of integration. The lower limit, the original lower limit was x equals 0. We're going to have u equals, when x is 0, u is 25, right? So the new lower limit will be 25. The upper limit, the original upper limit was x equals 3. Now when x equals 3, 3 to the fourth, that's 81. Times 9 would be 729, and then plus 25 would be 754. U equals 754. Right, so I'm going to make all these replacements, right? The limits and the u x, all the x stuff with the u stuff. Okay, so we've got 2 pi over 25, right? That's still out there. Integral from u equals, remember the new lower limit is 25, new upper limit is 754. And that's 729 plus 25. And here we have the square root of u, right? So u to the half, right? Instead of 25 plus 9 to the x to the fourth, right? That got replaced by u. U to the half. And then the rest of it, this dxx cubed, right? We said was 1/36 du, and I'm going to pull the 1/36 outside. Okay. Let's see, it's 754, a nice number. Let's see, 754. I'm just trying to see if this will be rational, because if that's not a nice square, perfect square, this will be good. All right, so this will be 2 times 377. 377 isn't a nice square. Yeah, so I'm gonna have to actually go through and do this by hand here. If it was ending up being rational, I'd go to Desmos, right? Because they want an exact answer. Okay, so this 2 here goes into 36 18 times, and 18 times 25, 450. So pi over 450 now out here. The 2 pi over 25 times 1/36. Integral from 25, 754. Double checking that's 754. 3 to the 4th is 81 times 9, 729 plus 25. 74. That's correct. Oh, I should just be doing the antiderivative right now because I know the antiderivative of u to the half. Sorry. So this will be u to the 3 halves, and then times 2/3. But I'm going to pull the 2/3 out here. Right? It's a constant multiple. And then we're going from 25 to 754. And then 2 goes into 450, 225 times, and then 3 times 225 would be 675. So we have pi over 675 out here multiplied by 754 to the 3 halves power minus, and then 25 to the 3 halves. Right, that'd be the square root of 25 is 5. 5 cubed is 125, right? So minus 125. That's actually a nice one. And there we go, right? Now again, they might rewrite this as 754 times the square root of 754, but this is it. This is your surface area, right? That many square units for the surface of rotation generated by rotating that curve around the x-axis. So surface area equals pi over 675, right, times the quantity. And we had 754 raised to the 3 halves power, then minus 125. That should be good. Great. All right, yeah, see they wrote it as 754 times the square root of 754, and then distribute the pi over 675, right? Get this. And there's your curve, right? Rotate it around the x-axis. You create this like tornado shaped thing, which you can look at moving the graph around, right? Right? And the surface area of that is this value here that we just found. All right, great. All right, so that's it. All right, there's a bunch of examples where you're finding arc length, the length of a curve over some interval. And a bunch of examples where you're taking a curve like that and rotating it or revolving it around the x-axis or y-axis to create a surface, and then finding the area of that surface. And as I said at the top of the video, right, just be aware that the questions I saw here are not going to be exactly the same as the questions you see, right? You might have different numbers or different curves given to you, but the procedure is the same, right? I'm hoping that they're similar enough that watching me do these here will help you out when you work on them on your own. All right, and thank you very much for watching.